Okay, let's start section 2. This section we are focusing on what is the TR2 or Technical Report 2 of ISA 106, which is basically focuses on work process. And you can see majority of this talk is about planning of definitions and requirement and design. And again, it focuses on procedural automation. Now, the main things that we can talk about it when we want to implement a work process, the best way is to use the V model developed by GAMP standards. And how do we relate this to our model here that starts with UM, EM, and CM? That's our focus area here. Therefore, if we go next, it assumes that you have a philosophy of procedural automation and you have toolkits to develop them. The first thing you want to do is to set the scope, specify the philosophy, the instant philosophy, which might be different from this one, define the work plan and toolkit. In other words, in the GAP environment, we can say this is how we define user requirement specification, and we refer to it as a URS. And it looks at the plant and plant area environment here. Now, if we look at the next part, we talk about procedure requirement, design implementation model, and test. If we translate that to GAMP model, it talks about functional requirement specification. Now we're getting down a little bit into UM and EM, and we refer to this as FRS. The next part, it refers to as implementation. And implementation is basically, we are talking about how do we convert what we define as FRS into SDS or software design specification. And then we develop the software and we go back and improve our philosophy and toolkits and we carry on for the next project. Therefore, in a nutshell, this is what ISA Technical Report number 2 does. Now, therefore, let's just go back to the V model. And basically, the V model says a customer, for example, Exxon or Dow, will have a project, wants to do process automation, and they define user requirement specification. This is a guideline at the plant level that says what is going to happen underneath. Then customers, sometimes with suppliers, will take this and now go a little bit detail at UM and EM level, define functional requirement specification or FRS. What is the hardware design specification, HDS? To be able to do these two very well, you need to know which software or which hardware you're going to select to develop your process control strategy. Therefore, once you've done that at this level, you have selected whether you want to go, say, with Yokogawa, Emerson, ABB, and then you write the software specification. Once you have done all of these works jointly or the suppliers, then the suppliers or some other groups will develop the code based on these specifications. You develop the unit code and then they check it. They make sure everything works, and then it comes back to you, and you check it and make sure everything works. And then basically at the end, you're doing performance qualification at the very end. Therefore, everything, all of these things that you define is working here. Now, all of the things I'm discussing here is coming from two sources that are accessible. One source is this startup company that has 3 areas, industrial process control courses that are listed there. And it's basically being taught, some of them, at McMaster University. I'm adjunct prof there for postgraduate course and called Process Design and Control for Operability for the last 10 years. And I teach this course 1 term. Then we have a package or a set of procedures or toolkits that it enable a user to define user requirement specification and functional requirement specification for unit module. Therefore, this is there. Then we have another package called control builder that it basically translates this design criteria into the final product. For example, if you have ABB and you finish this part, then automatically it will generate up to 90 to 95% of the code from your design document. Therefore, we don't have any barrier between what we are designing and what we are getting. Therefore, these are the references for the next sections of this document. Now, let's talk about how we can develop a URS. It's divided into 3 segments. One is how to build and how to review the CM, then how we define the URS, and how to review URS to obtain financing to go forward. Therefore, what does that mean? That means that if whatever project you do, you need to have a basic set of building blocks. We call them CMs. And if you remember, these CMs are basically a building block of process control applications. And as we discussed before, they should have enable logic, disable logics, parameters, code, visualization. Therefore, we assume we have this, or you have developed a library from the vendor that we have this list. This is a very simplistic list, but it's actually very sufficient to do majority of the work, up to 90% of the work that we want to generate automatically. Therefore, this is the list. And if I look at one of them, for example, look at these alarms. Therefore, what we have here is we have a parameter name, and then we have a data type, and then we have the initial value. What is the initial value if you don't do anything with it? Each CM should, because they are building block of our application, therefore they should have a parameter list as I'm showing. It should have an associated code with it, and it should have associated graphics with it. I'm not covering these two in this lecture. Now, if we look at the URS, just think about URS as 9 sort of parts that we want to put together to be reviewed by operation, by the project team, and therefore that sets, and usually the process automation leader does this work, and it's a document that you submit to the project team to get financing approval to go ahead with this project. Therefore, you should have a process description. Again, very simple process description in a sense that the process control engineers, the operation can read this and understand what does this process do. It should not be as complex as Aspen or simulation documentation or design documentation. Very high level documentation here. The next thing we need to have is we need to have a process diagram. Process diagram is very useful because basically it's drawing these things in Excel is less than half an hour because we have all of these objects. Therefore, we just connect them together. And it's very important when you draw these, therefore, you need to draw it such that it becomes a vehicle of communication with operation and get their point of view into the design, because without that, you are not going to be successful. Therefore, here what we have is we have feed coming to the first reactor, going to the second reactor. We have another feed coming here, going to the third reactors, and then we have a heat exchangers, and we have a recycle line coming out of this system. Therefore, as you can see, this feed goes down to tower 1, tower 2, tower 3, and then in tower 2 it comes back, and the heat of the top products is used here and go back as a recycle throughout the reactor system again. Therefore, this is a very complex process, and look, the feeds are about 1,500 and the recycle is 36,000 units. Therefore, it's very important how we're going to start this up, because your control strategy, all of these unit operations or procedural control depend upon what is a scenario that you want to start this unit. Therefore, in the part of doing that, number one, you need to say what are the units. Therefore, and in the units, we have divided this process into 8 units. And there are 2 types of unit. There's a standalone unit like this one that we develop. We take a standalone module and we modify it. Therefore, we build a URS for its standalone module. And then we generate to library, we generated a generic name convention, for example, for this tower. And then from this, we will instantiate it. Therefore, we say this will take 100% of unit work to do this. There is another type that we have lots of time. We have one unit like this tank that the other tank is identical except the IO is different, but everything else is the same. Therefore, we have a master, we modify the master, we generate the unit in the DCS system once we have done this, and we instantiate it as a UM. Therefore now, but we give it about 120% work compared to this one. Because it's a master, we need to worry about lots of little things. But when we instantiate its copy, we just give it 20% of time. Therefore, what happened here is that when we do unit definition, especially identifying who's the master, who's a copy, and who's a standalone, we save lots of money and basically we make our product better. Because if there is some mistake here, then you fixing it here, both of them are going to get fixed. Therefore, in this project, we are saving 22% of overall cost. Therefore, if we look at now, this is most important part of the URS. Every unit that we look at the plant level, we need to have an agreement how we start it up, run it, and shut it down. Basically, as you can see here, we have number of these MVs. Each of these rows represent an MV, and this part is we are starting up the unit, and these are all of the MVs, and the diagrams have been marked. Then we go to run, and basically in run, lots of things happen. For each of the MV, they are different, and then we go to shutdown, and then we shut the process down and we can start it again. This document, when is printed as a 19 by 11 or bigger, color and review with operation, it has significant impact in the way that we will not fall or we will not fail or everything works according to plan, because this becomes the master recipe how this plant is going to be operate. It's very complex, and therefore you need to have something you refer to and get the timing right. Now, if I look at the next page, I just expanded some of it, and as you can see, these are the MVs that we talked about, and therefore this is beginning and we're going forward in time. This is the diagrams that I showed you. Therefore, if you look at it, we say we are going to start this stream 1, which is this one, butane feed, and we are going to ramp it up. These ramps are not actually correct. It just says go from 0 to something and then carry on. And what we are saying here is it will take 2 hours, yes, to do this part. Then we are filling R and C506. Therefore, we're filling this. Then we go and fill the other one. If we look at it, therefore, this is number 2. We fill number 2. And then we go, because of this, we need to make sure that we send things down to the distillation. We heat up the distillation and we run them until we get from the second distillation, we get this stream back and this recycle goes through the whole system. Therefore, you spend a bunch of times to go through this part, which is the startup, and how to get the recycle up and running throughout all of these and then we go to the run step. Therefore, again, this has tremendous value. At the URS, you're only looking at NVs and diagrams to do this operation. The next thing is control objectives. You need to specify for the control engineers that what is the objective for these 7 different categories. What's your objective in safety, environmental protection, equipment protection, a smooth plant operation, product quality, profit optimization, and monitoring and diagnostic. In that order, it's critical that you define what is needed. And this comes from Tom Marling, my colleagues in McMaster, a very good book on process control. Last but not least, therefore, we have the IO allocated to URS, and that's the finishing of the URS. We do estimation of the cost, and we review the issues, and then we have finalized the URS. Therefore, what we discuss here is a TR2, V model, control module basic block, URS, and 9 different portions of the URS that we need to check.